Hello everyone, I'm Bashima. I recently received my PhD from UNC Chapel Hill and I'll be joining Worcester Polytechnic Institute as an assistant professor. Today I'm here to present my work, BreathTrack, which I did during my internship at Samsung Research America with my mentor, MD Mahbubur Rahman. This pandemic has changed the world as we knew. It is difficult to make peace with the devastation this pandemic has brought and so many deaths around us. But COVID-19 is not the only respiratory disease that takes so many lives. Every year, millions of people die from other respiratory diseases such as chronic obstructive pulmonary disease and asthma. Researchers have shown that continuous and passive monitoring of breathing biomarkers is essential for the management of respiratory diseases. Recent works have found respiratory rate and shortness of breath to be significant symptoms for COVID-19 early detection. Traditional monitoring devices are costly and can only monitor severe patients admitted in hospitals. They cannot continuously monitor for detecting diseases early or predicting deterioration in mild patients' health. Wearables such as chest bands and mobile spirometers are uncomfortable for long-term wearing or require additional user effort, making them unsuitable for continuous and passive monitoring. Now, if you look around, you will see almost everyone has a smartphone in their hand, which makes it a cost-effective and suitable candidate for continuous monitoring. Prior works have used smartphones for guided breathing exercises, respiration rate estimation using motion sensors, and cough and sneeze detection. Despite the commendable efforts and results, these works have bad draws. Most of them require additional effort like forced exhalation, which have proven to deteriorate health condition. Though the work of passive wheeze sensing are promising, wheeze is only present in severe patients and cannot be heard for mild or moderate patients. Finally, active effort is required to enable the system that uses motion sensors, which makes them unsuitable for long-term passive monitoring. Microphones in the smartphones make a perfect candidate for passive monitoring, and previous work have shown commendable results with audio data where they focus on breathing exercises and annotated datasets. However, for early detection of respiratory diseases, we need to focus on regular uncontrolled breathing, which will be passively monitored. Now, for regular uncontrolled breathing, it is hard to get labeled datasets because labeling inhalation and exhalation phases in regular breathing is hard due to the inaudible parts at the edge of each phase. Thus, we introduced BreathTrack, which takes audio breathing data as input and detects the inhalation and exhalation phases as output. Here, the main challenge is how to develop a breathing phase detection model with an annotated dataset. We use the knowledge from the motion domain from the smartphone's IMU to train the acoustic model using teacher-student training method. Now, another question is, now do we need to annotate all this motion data? That is also a tiresome and unscalable solution. To eliminate the burden of annotation, we combine deep learning with signal processing. We redesigned the teacher-student model where during training, the input to the teacher model is the motion data, which goes through a signal processing model, unlike a deep neural network model in traditional teacher-student training method. And then we train the deep neural network of the student model that takes the audio data as input. During inference or runtime, only the audio data and the student model is used to get the breathing phases. Due to timing constraint, in this presentation, I am only showing the comparison of BreathTrack with Brace, a state-of-the-art algorithm that uses acoustic sensor for breathing phase detection during breathing exercises. Now, in breathing exercises, we know the duration of inhalation and exhalation, there are intentional pauses between them, and we know that the user is breathing in through their nose and out through their mouth. None of this is present when we are working with regular breathing. Despite that, we see that BreathTrack performs better than Breathe in regular breathing because we are using the knowledge from the motion domain that allows us to work good in the edge or inaudible sections. Now, using these breathing phases, we can measure the biomarkers, and we can use it for many other purposes. As an example, we show that we can achieve up to 76% accuracy to detect different types of respiratory patients. In summary, we propose a technique that can be very useful to monitor respiratory patients, including asthma, COPD, and even COVID-19, remotely using their own devices. Our technique does not require additional effort or any burden of annotation of the training data. This is a stepping stone towards passively monitoring respiratory patients using audio sensors embedded around us.